So, welcome to this playlist of Dwave quantum computing, and here we are trying to explore the quantum annealing aspect of quantum computing, right? And you can see in the previous video, I helped you to install the Ocean Toolkit by Dwave System, and using the same toolkit today, we will write the Hello World quantum program, which is the basic thing that we will write, and then we will build upon it. So you can see last time we created this test file just to test the installation, and today we will write the hello world program in the same file. So let's do it. And yeah, do this. And I'm using VS Code here, Visual Studio Code, but you can use any editor of your choice. So first things first, let's just rename this to hello world. Okay, and I'll name it here as well. I have increased the font size so you can have a look. Hello world. Yeah. Then of course the first comes the imports. So we will import. Yes, this is what we'll require today. And there are different packages, and every package has its its own working and functions. Today we'll be using that one. So the second thing that comes, of course, is the solver. So let me just get the solver, and then we will talk about it. Diamond dot exec solver. Yes. Okay. So let me tell you about what this exec solver is. So if the problem is quite small, like 1 or 2 qubits. So the problem that we are going to solve today in this hello world program is just consists of 2 qubits. So such small problems can be simulated on the CPU itself of your own computer, and exact solver does that for you. And the other aspect is that if you before you are submitting your problem to quantum computer, you want to make sure that everything you've done is correct. So exit solver can also be used for that. And exit solver actually gets slow if you cross that limit of 18 qubits. If you are solving a problem of where the number of qubits has surpassed 18, then it will really get slow. Otherwise, it can work fine. And yeah, that's the purpose of exact solver. The two purposes are that small problems can be solved directly on exact solver because if you are using quantum computer by D-Wave, then you will be charged for that. So you want to reduce your cost as much as possible. And the other thing is that even if you are submitting a problem to quantum computer, you must make sure that there are no errors on your side, right? So that can be used for it. And now comes the more important part. Define the Cubo. So this Cubo stands for Quadratic Unconstrained Binary Optimization Problem. And Cubo is a very closely related to Ising model. And we will get to that theory in the next video. But think of Cubo as, a way of formulating your problem. So you are trying to solve a problem using quantum computer, and Cubo is the way formulating that problem so a quantum computer can solve it, right? So let's see what this quantum that is Cubo actually looks like. All right, and let me just define the Cubo for you. So note that I'll be using 2 qubits here. So this one will be -2, and let me just write it quickly, so that I can. So this is a simple Python dictionary that I have used to define the Cubo. And you can see there are two variables here, A and B. Both of these you can think represents qubits. All right, and when you formulate so what here is going on is that I'm trying to favor these two qubits, trying to take the same value. So I don't want the qubits to take a different value from each other. So we know that the qubit can take 0 or 1. So I want the qubits to take the same value, whether it's 0 or 1. I want that to happen. So that's actually the way of formulating the problem. And actually, the problem can be quite different, but we'll get to that later. But just understand that we have just formulated a Cubo for some actual problem that we were trying to solve, and the solution looks like that we want the qubits to take the same values and not the different values, right? So that's one point. And now we need to get the BQN. Okay, let me just write the code first and then I'll explain. So again, mod binary quadratic model from Cubo, that's right. Okay, let me explain this line of code now. So you defined a Cubo, and to solve it you need a binary quadratic model. Actually, this binary quadratic model is nothing but a Python class. This is provided by DieMod. So what you're just doing is that it's a good, easy way of solving the problem. That's it. It just takes your Cubo as the that you have defined here using this Python dictionary, and it takes it, and now it will help. Now it can work in harmony with the solver to solve this problem. So let's do that. Okay, we've got the BQM as well. Now let's solve the problem. So we will just results, and then what we'll do is we'll take our solver that we defined previously and sample BQM. Okay, that's done, and of course we want to have a look at the results. So what we shall do is just go ahead and print the results. So again, let's go through this. We imported DieMod. We defined our exact solver. I told you what this exact solver is about. Then we took a problem where we wanted the qubits to have the same values, and then we defined a cubo. We got some values here, and we will see how these values show up, how this -2 1 1, how you get these values. We will see it in the upcoming videos, and it just involves simple mathematics, nothing to worry about. And what you do is you pass this defined cubo, and you get BQM. You solve it using your solver, you get the results, you print them, and let's get the results. So actually I can show you so that we can analyze the results. It's running. Yeah, we got the results, and let me just copy and paste it here so you guys can see it. Okay, paste it here. Okay, so you can see here that in the first two rows I have got just look at these A and B columns. So you can see they are having the same values, and the energy given is 0. And for the other two possible cases, 1 0 and 0 1, where they are having different values, the value given is 1. So how do you interpreting results is that the lowest value you get is the ground state. So what you're doing this with this quantum annealing is you are trying to find the ground state, and this finding the ground state is like minimizing a function. It's just like that, and the lowest energy you get is the ground state. Okay, and that's the solution that the computer is trying to tell you. The other values you get are called the exciting states or excited states, and you can see the value here is 1, which is higher than 0, right? So this 0 is the lowest state, lowest energy, and so the quantum computer what is trying to tell you that this is your solution, and that's what we were actually wanted. That's what we were wanted, right? Because we were trying to favor when we were creating the Cubo, we were favoring these qubits to have the same uh, values, right? So what we got is what was expected, and that's the simple Hello World program using Ocean Toolkit of Dwave Quantum Computing, Dwave Systems, sorry. And that's it from this video. In the next video of the playlist, we will get into the mathematics and see how this Cubo, what is this Cubo first of all, how do you formulate it, and that's it. So if you like the video, you actually can like the video on using that like button, so that the YouTube can help more people by recommending this video to them. And with that said, I will meet you next time in the next video.